Okay, this is part 2 of our algebraic coding tour. And now we talked before about repetition codes. Here's an example where you're actually trying to send one bit, 0 or 1, but the code word that you send has 3 bits. So instead of sending a 0, you send 0, 0, 0. Instead of sending 1, you send 1, 1, 1. Okay. Now this table indicates the results of the transmission. If there are 0 errors and 0, 0, 0 is transmitted, then 0, 0, 0 is received. If 0, 0, 1 is received and 0, 0, 0 is transmitted, you have 1 error, and so on. That's what this table shows. Okay. So in order to decode the received word, suppose you receive 0, 1, 1, for instance. You know that that has errors in it because that's not one of the possible transmitted code words. But you look in this table, you find which code word yields the least errors, and that's how you decode it. Okay. If there's only 1 error, then that code word is decoded correctly. If more than 1 error, then it's not decoded correctly. Now, why do you decode to the code word that has the minimum number of errors? Well, that's the most likely one that was sent then. Here's a picture of what's called a binary symmetric channel. This over here on the left-hand side is what's transmitted, and this is what's received. All right. Actually, most practical communications channels aren't at all like this because the error changes from bit to bit. You have time varying noise, but this is a very simple case that illustrates some important concepts. Okay, so what this says is if 0 is transmitted, then there's a probability P that 0 is received and a probability Q that 0 is not received. On the other hand, if 1 is transmitted, there's a probability that 1 is received and a probability that, that 0 is received. Okay, so notice that this Q is the error probability, the P is the no error probability. It's the probability that any given bit will be transmitted correctly, and Q is the error probability. Okay, now usually, in fact always, Q is less than P. The probability of error should be less than the probability of transmitting the correct bit. If Q equals P equals 1/2, then you're in trouble because then all you receive is going to be noise. No matter what you sent, you have a 50-50 chance of receiving 0 or 1. Okay, so you compute some probabilities down at the bottom. Unfortunately, these error probabilities add up very quickly. Suppose P equals 0.999. In other words, you have a 999 out of 1,000 chance of transmitting a correct bit every time you transmit a bit. And suppose you send 10,000 bits. How many errors do you expect in that string of 10,000 bits? Well, think about it for a second. Well, to get all 10,000 bits correctly, you'd have to hit the 999 out of 1,000 each time. So each bit has a high probability of being transmitted correctly, but if you're going to get each bit correct, you'd have to multiply that probability 10,000 times. That's a very, very small probability. So a message this large is almost certainly going to have an error in it. So this theorem has to do with standard probability. If you've had probability, you've seen expressions like this before. This is the probability of k errors and n minus k non-errors. Okay, just a typical binomial probability. P is the probability of 1 non-error, Q is the probability of 1 error, and out of n total bits, that's the probability of k errors, n minus k non-errors. So I'm not going to go through this proof. This that's a standard probability proof. All right, it's interesting to look at this example 4 because you get some practical probabilities. All right, suppose you have 0.995. That means 0.5% error on each bit. 500-bit message is sent, then the probability that there's no error at all is less than 1 out of 10. The probability of exactly 1 error is roughly 1 out of 5. Probability of 2 errors is roughly 1 out of 4. Probability of more than 2 errors is almost half. Okay, well, we want to develop some fancier methods than repetition to create codes that can correct errors. And we're going to use this thing called block codes. And this is kind of reminiscent of what we did in cryptography, where we encoded 2 bits at once. If you remember, we would encode 2 bits at once by multiplying by a matrix. If we had letters, for instance, and we had 26 possible symbols, then we would do this matrix multiplication mod 26. We'd have numbers from 0 to 25 in here, and then we'd have 2 numbers from 0 to 25, like you might have 23 and 2, and you multiply by some matrix that has entries from 0 to 26, and then you get results over here that have entries from 0 to 26. And it's better to use prime modulus, or you run into troubles. But that was a method of encoding more than 1 bit at once. So now we're going to encode more than 1 bit at once in a somewhat different fashion, but there's some similarity. Okay, so here's how we define an encoding function. The encoding function goes from Z2M to Z2N. What is Z2M? Z2M is equal to M binary bits in a string. It's a string of M binary bits. Okay, you could represent that as x1 ... through xm, where each x, where xj is in Z2. Another way of representing Z2M can also be written as Z2 cross Z2 cross ... cross Z2, and there's M of these. All right, now the encoding function takes a string of M binary bits to a string of N binary bits. This is like in the picture that we mentioned above. So this corresponds to exactly what we were talking about here. An M-digit message gets encoded into an N-digit code word. Now, of course, to recover the original message, you need a decoding function. In order to be a decoding function, then I should be able to take code words in Z2, these are the coded words, into original code words. Okay, so here he says a code word is any element in the image of E. These are the transmitted code words. Okay, so we require that E is 1 to 1. So the 2 information blocks will not be encoded into the same code word. If our code is to be error correcting, then D must be on to. So what that means is that any time I receive any sort of code word, I should be able to assign to it an original word so I know what to decode it as. All right, let's look at this example. Even parity coding system. Okay, what's the encoding function? The encoding function of 7 binary digits is x8, where x8 is the binary sum of x1 through x7. In other words, if there's an even number of 1s here, then x8 will be 0. Odd number of 1s, x8 is going to be 1. So that's the encoding function. What's the possible decoding functions? Well, we don't have that here. Okay. Remember we said that the parity system can only detect errors, it can't correct errors, so it may be difficult to figure out how to decode a message that has an error in it. Some more terminology. Let's suppose we have 2 different strings of binary digits, 2 different binary n tuples, or we can also say that's 2 different code words. The Hamming distance between these two, it's also called the Manhattan distance in other contexts. It's basically the number of bits in which x and y differ. Okay, that should be pretty clear. All right. Now the minimum distance for a code is the minimum of all distances between distinct code words, and we'll see what that means in a minute. Okay. Just to recap that, the Hamming distance is the number of bits in which two code words differ. The distance, the practical interpretation of this Hamming distance is the minimum number of transmission errors required to change one code word into another. So it basically tells how hard it is for noise to change one of those code words into another. If two code words are close to each other in Hamming distance, that means that it's relatively easy for noise to change one of those code words into another. So it's better to have code words that are far apart. All right. The minimum distance of a code is the smallest of all distances where X and Y are distinct code words. You want a code with a large minimum distance. For instance, if the minimum distance is 4, then it would take 4 errors for one code word to be transformed into another code word. That's good, because then you'd have to have at least 4 code words to make a definite undetected mistake. All right. The weight of a binary code word is the number of ones in the code word. So the weight of the 0 code word is 0. All right, let's use this terminology in some examples. Here we have 1, 2, 3 code words. All right, you can calculate the Hamming distance. For instance, the distance between X and Y. Well, they don't differ in the first digit. They differ in the second, third, fourth, and fifth. So they differ in 4 digits. That's why you get this distance here. So we have that Hamming distance for those two code. As far as the weights are concerned, weight was the number of non-zeros in the code word. So for instance, the weight of X is 3 because X has 1, 2, 3 ones. Okay, so that's the meaning of that terminology. All right, so here we have some basic properties of relating weight and distance between code words. Okay, let's go through these properties quickly. The weight of a code word is the distance between the code word and the 0 code word. If you think about it, that falls right out of the definition of weight and distance. The distance between any two code words is bigger than or equal to 0. Think about what the definition of distance is. It's the sum of digits where they differ, so that's got to be positive, or 0. The distance is 0 exactly when X equals Y. The distance between X and Y is the distance between Y and X. And the distance between X and Y is less than or equal to the distance between X and Z plus the distance between Z and Y. All right, so that one's probably the trickiest one in this sequence, but it does make sense if you think about it. If you want to understand, write down 3 code words and see how that works. Okay. Here it says the weights in a particular code are usually much easier to compute than the Hamming distances. So if a code is set up carefully, we can use this factor advantage. All right, let's look at this particular example. All right, so for instance, suppose we have 2 code words that differ in only 1 digit. That means the distance between them is 1, so a single error could change one to another. So this code, a code that includes both of these code words, cannot even detect a single error. However, if you look at all 4-bit code words, where the first 3 bits carry information and the 4th is a parity check bit, if you look at that table, you'll see that the minimum distance between any 2 code words is 2. So that means that it takes 2 errors to change one code word into another. If you have only 1 error, there's actually a mistake here. If you have 1 error, you can detect the error. It's not a single error correcting code. It's a single error detecting code. Okay. So the nice thing is that all you need to do is analyze the distance information to tell how the detection and correction properties of a code. Okay, you can read through the discussion. The upshot is this. Let C be a code where the minimum distance is 2n plus 1. Then C can correct any n or fewer errors. Furthermore, if any 2n or fewer errors occur, then they can be detected. And there's a very simple proof of this. Suppose you have let me represent the 2 code words like this. The distance between them is 2n plus 1. All right, to be continued.